The purpose of this lab is to test Newton's second law, which says, in the absence of a positive or negative net force, an object will move at constant velocity. To do this, an object moving at constant velocity in a constant direction will be observed and recorded. The computer program Tracker will then be used to import the video recording, track the motion on screen, and create a graph of the motion. Python will then be used to create a computer model that simulates the motion of the object. Once we have these two models, we can compare them together to prove or disprove Newton's second law, which is stated as Vf equals Vi plus Fnet divided by m times delta t, where Vf equals final velocity, Vi equals initial velocity, Fnet equals the total net force acting on the object, m is the mass of the object, and delta t is the change in time from beginning to end. In this lab, we are concerned with the total net force equal to 0. So taking a closer look at Newton's second law, we can see that whenever there is a net force of 0, no matter what the mass of the object is, or no matter what the change in time is, Vf will always equal Vi. In other words, the object's final velocity will always equal its initial velocity. There will never be a change. This is consistent with the momentum principle, which states that delta p, the change in momentum, is equal to F net times delta t. Similarly to Newton's second law, when F net equals 0, delta p will always equal 0. There will never be a change in momentum. Moving over to the Tracker program, we can see that the object we are observing is a cylindrical can with a mass of 0.198 kilograms, and from the calibration stick we can see that it has a diameter of 0.05 meters. The motion we are interested in is the translation of the can, so the average position has been created as the can's center of mass. This has also been set up as the origin of our axis, and you can see that the axis has been shifted 1.8 degrees up from the horizontal to follow the can's center of mass as it rolls. From the data collected, we can see that as time increases, the x values increase in the positive direction. This is because the object is rolling from left to right in the positive x direction. Had we shifted the axis to the right and had the object roll from right to left, these x values would be the same, except they would be negative. Similarly, had we rotated the y-axis down and had the object roll in the positive y or negative y direction, these same x values would be in the y value column, and they would be positive or negative respectively. How you shift the axes and how you declare the axes does not matter and does not affect the object's motion. The only thing that is changed is how the motion of the object is described. Using the data from Tracker, we have calculated the initial velocity of the can. We have done this by taking the second x position minus the first x position of the object divided by the second time minus the first time, and we have gotten an answer of 0.20 meters per second in the positive x direction. The final velocity is calculated the same way, except using the last x position minus the second to last x position divided by the last time step minus the second to last time. Using this initial velocity we just calculated and the initial position from Tracker, we plug these values into our computer model in Python that uses Newton's second law to calculate and graph the position of the object over time. When we run the code, we see that the graphical representations are very, very similar to what we saw in Tracker. Now, moving over to our Google spreadsheet, we can see that we have compiled the observed values from Tracker along with the calculated values from our Python computer model. And we have graphed them on the same position versus time graph. We can see that these two models have a positive slope, and that is because we chose to have the object roll in the positive x direction. As stated earlier, had we chosen to orient the axis on the right hand side and have the object roll from right to left in the negative direction, these same slopes would be negative. It is also important to note that the computer model is of a perfect frictionless world. However, the experimental model is a model of the real world in which there are many pushes and pulls acting on the object, including friction. Because of this, the experimental position should be less than the modeled position. However, near the end of the graph, one can see that it is slightly greater, and this can also be seen in the 0.006 meter per second increase in the final velocity over initial velocity. However, this can be attributed to human error using the tracker program when calculating the center of mass of the can, as it is difficult to get it perfect every time. Nonetheless, these models are nearly identical and show that in the absence of a verifiable positive or negative net force, the object's final velocity did indeed stay the same as its initial velocity. Newton's second law is verified.